This is physics. This will help you how to solve problems, as well as it will it will be a good revision for you. At the same time, I will be dealing with only the basic points. I will be dealing with only the basic points. And this is a phase one. This is part one. Again, there will be another video, that is part two. So here, let us start. Means it will help you to solve problems. These are the basics. Suppose there are two blocks. These are the two blocks, M, capital M, and small m, and they are tied by a wire or a rope. Now, if you apply a force F here, so what will be the acceleration? Now, here, when you are going to find acceleration, then you have to consider this whole as a system. This whole as a system. And now, therefore, your F is equal to m E. This is your formula, but here your m will be m plus capital M into A, and you can find the value of A. So here, this is considered as a system. And the acceleration that you are going to find here, this force will be given to you, this and this will be given to you, but you have to find the acceleration. So here, this whole is considered as a system, one system, it's one piece. And so the acceleration that you are going to get here, this will be the acceleration of this as well as this. Both will have the same acceleration. And here the tension will always act opposite to the force. So this is the basic. The basic is that you have to consider this whole as a system. And the acceleration of this body will be also A, and the acceleration of this body will be also A. Now, second point. Suppose here this is a truck, this is a truck, say, this is a truck, and on its platform there is you have kept a box here. Now, this is moving as a force is applied here, it is moving uh, in forward direction. Now, here the main question is that, the main point is here, that the block must move together with this vehicle. The block must move together with this vehicle. And suppose the frictional force is given here. So the frictional force is given here. This is the platform of your truck, and this is the box. So here this is the force applied here. So not, let me take, this is the platform of the truck. This is the platform of the truck, and a force is applied here. And suppose the friction is given here. The friction between the block and the platform of the truck, it is given to you. Friction between the block and the platform of the truck given to you. Now, F force is applied here. But the question here is that this block must move together with this vehicle. And the frictional force between the block and the vehicle, it is given to you. So, in this case, the frictional force will be in this direction. And in order to balance this force, there must be an equal and opposite force, and that force will be F is equal to ma, and this is called the pseudo force. This is called the pseudo force. Now, next type of question. Suppose this is a pulley here, this is a pulley, this is a pulley, and this is a rope here, and one it is a M, and other is a small m here. This, sorry, this weight is acting downward, that is mg, and here this weight is acting downward, that is mg. Now, so tension will be here, this is the tension T, and here this is the tension will be T. Now, if the block is moving in downward direction, so with some acceleration a, and therefore it will move in the upward with some acceleration a. So here the main point is that the acceleration remains the same and the tension remains the same. So first of all, you have to take the force analysis of this point, and then you are going to take the force analysis of this point. And whatever the question it has been asked to you, you can solve it. But the main point I want to tell you here, this is the tension will remain the same, as well as the acceleration will remain the same. Now my next question is, suppose it is of this type, say this type. Here this is a pulley fitted here, and here this is a block of some mass m, and say another, here this is a pulley, another block of mass small m, and here this force is applied here, F force is applied here. So here this is the rope, this is the pulley, and force applied here. If you see from the main point here is that if you see from the rope, side, if you see from the rope side, the acceleration of these two will be the same. If you see from the rope side, the acceleration between these two will be the same. This is an important point. The force F is applied here. So if you see from the rope side, your acceleration of this body and this body, they both will be the same. Now let us take an remember that if it is an elastic collision, if it is an elastic collision, if it is an elastic collision, if it's an elastic collision, then your momentum, your momentum is conserved, as well as your kinetic energy is conserved. That means momentum before collision is equal to momentum after collision. That is, momentum before collision is equal to momentum after collision. After collision. This is the now say let us take motion in a circular a motion in a circle. Motion in a circular, it will be better to say motion in a vertical circle. It will be better to say that is motion in a vertical circle. Let me rub this and move to this point. Motion in a vertical circle. 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 That means this is your body of some mass m. It is moving in a vertical circle like this. Means this is a, say, a rope tied with a, or a string tied with a body of mass m, and it is rotating in a vertical circle. we have to determine the motion. So here in this direction, it is moving in this direction. So here, let this point be A, and diametrically opposite, let this point be B. So here, the velocity will be in this direction tangentially. So let this be VA, and here, let this be VB. So let us see one analysis, that is, at any point P here, it is making an angle theta with the vertical. So here, the body will be vertically downward, that is mg, and the reaction will be in this direction. No, we can't say reaction. That means uh, component of mg. That we can't say reaction. Sorry, reaction. This is theta. So the component, because this is vertically downward, this is vertically downward. So these are parallel. So this will be theta, and component of mg along this will be mg cos theta, and this, that is along this direction component, this will be your mg sin theta here. And this is the tension of the string. This is the tension of the string. So when it is moving in a circular path, here comes our centripetal force. Centripetal force. Here comes our centripetal force. So your centripetal force, that is mv square by r. Suppose this is the radius is your r, mv square by r. That is mv square by r. This will be equal to the resultant of these two forces. One force is acting in this direction and tension is acting in this direction. So T minus mg cos theta. So here your tension will be mv square by r plus mg cos theta. This will be. So this will be your tension. So this will be your tension. This will be your tension. Now at point A, at point A, at point A, you can take tension or the tension in the string. That will be tension in the string T. This will be is equal to mv a square by r, because the radius length of the rope is r, and your theta is 0, so this will be plus mg cos theta 1. And at point B, at point B, at point B, your theta is 180 degree, so your tension will be mv b square by r minus mg. So these are the basic points. These are the basic points, because you know that when a body is moving in a circular path, there is a centripetal force which acts towards the center of the circle, and the centripetal force is this, and the centripetal force will be the resultant of these forces. Resultant of these forces. And at point A, since theta is 0, theta is 0, so your tension in the string will be this. And at point B, because it is theta is 180 degrees, so your tension will be this. Now we go to torque. This is an important part, torque. Torque. That means it gives a rotational effect. It gives a rotational effect, that as torque, as only the formula is r vector cross f, and this torque acts perpendicular to the r and f vector, and it gives a turning effect. It gives a turning effect. So it is also called as the moment of a force. It is also called as the moment of a force. It is also called a moment of a force. Now, let us take an example here. A rod, anything, say a leather or a rod, something, it is resting here. So let this point be B and this A. Now a weight is acting vertically downward, W, and this is M. So the reaction here, this is perpendicular to this NA, and the reaction here is perpendicular to B, this is NB, perpendicular to this. Now what happens here, now if the question, in the question it is rotational equilibrium, remember, if in the question it is rotational equilibrium, if it is rotational equilibrium, then we solve it by the help of torque. If it is in rotational equilibrium, then we solve it by the help of torque. So let us take the moment of a force, that is, let us take about the point B, about about point B, about point B. So here you find that this will be W into Bm, that is equal to Na into Ac, Na, that this normal reaction into Ac, because your R is always perpendicular to the force. So you can solve this problem by the help of rotational equilibrium, and in rotational equilibrium, that means by the help of torque. When there is a rotational equilibrium, we solve the question by the help of torque. So I am only telling the basics how to solve the problem. The basic things I'm just dealing here. Now one more important thing about torque. When your torque is zero, that means your angular momentum, angular momentum is constant. Angular momentum is constant, and your angular momentum, that is equal to R cross P, where P is the linear momentum, and so your L is equal to R P sine theta. This is your when torque is zero, that means when there is no external torque. Torque zero means when there is no external torque. When there is no external torque, that means your angular momentum is constant. Now, similarly, you can also uh, that means angular momentum R cross P. This is the linear momentum. This is the linear momentum. Now let us go to radius of gyration. Radius of gyration. Gyration. Radius of gyration. And its formula is uh, radius of gyration, that is I is equal to, if I, that is mk square, that is k, it is the radius of gyration. And suppose if the momentum inertia of a body is I is equal to half mr square. Suppose this is the formula for a radius of gyration, that is the moment of inertia is equal to m into k square, where k is the radius of gyration. And suppose I is the moment of inertia about some axis. Suppose this is the moment of inertia. So here your k square will be is equal to r square by 2. So your k will be r by root 2. This is very important. This is way, in this way we find out the radius of gyration. Now let us come to gravitational potential energy. Gravitational gravitational potential energy. That means gravitational potential energy of a body. This gravitational potential energy of a body of mass m, and which is at a distance r from the center of the earth, which is at a distance r. The gravitational potential energy of a body of mass m, which is at a distance r from the center of the earth, from the center of the earth, gravitational potential energy of a body of mass m, and which is at a distance, and which is at a distance r, which is at a distance r from the center of the earth, is minus, this is minus g m m by r. And the negative sign, it a negative sign, it represents that there is attraction. Negative sign represents that there is attraction. There is attraction. This is the gravitational potential energy. So that means the gravitational potential energy of a satellite. Let us take the gravitational potential energy of a satellite, which is at a distance r from the center of the earth. Means instead of this m, we have taken any body, and let us take that it is the mass of a satellite. So its potential energy will be for the satellite also. It will for the satellite. 1 minute. That your gravitational potential energy of an Earth satellite will be Earth satellite, that is minus gm m by r. It will be same, where m, it is the mass of the satellite. Satellite. It is the mass of the satellite. And it is at a distance r from the center of the Earth. And your kinetic energy, and the kinetic energy will be when it is at a distance. Here r is the radius of the orbit for satellite. For satellite, here r is the radius of the orbit. R is the radius of the orbit, and your kinetic energy will be g m m by 2r. This will be your kinetic energy. Means here your m, the same formula here, that is the m, it is the mass of the satellite, and the means potential energy when it is at a distance r from the center of the earth. So it is this. Here your r is the radius of the orbit, and yeah, the kinetic energy at that point will be, this is your kinetic energy. So here your total energy will be kinetic energy, total energy. Here your total energy will be, your total energy will be potential energy plus kinetic energy, and it will come out to be that is g m m by 2r minus g m m by r. So here your LCM is 2r. So it comes out to be minus g m m m. This is comes out to be minus g m m. Capital M, this is your capital M, this is the mass of the earth, and small m, this is the mass of the satellite, and r, it is the distance of the satellite from the center of the earth. Now here there is an important point here, that is if we take, suppose if we take, that is the satellite is at a height. If we take the satellite, it is at a height. Your satellite, if you take your say let me write here. If you take the height of the satellite, height of the satellite, height of the satellite is equal to the radius of the earth, radius of the earth. Height of the satellite is equal to the radius of the earth then your total energy will be equal to minus gmm by 2 r, radius of the earth. This is radius of the earth, so this will be minus gmm by 4r. This capital R, this is the radius of the earth. Now here, since the total energy is minus, that means it is the binding energy. This is the, because it is minus, this is the binding energy of the satellite. Binding energy, this is the binding energy of the satellite. This is the satellite. This is the binding energy of the satellite. Now, why I have selected this, the most important thing here is that if the satellite is ejected at a height equal to the radius of the earth, there is acceleration due to gravity is still exists there. Your acceleration due to gravity still exists there, because we know that your g, we know that g is equal to gm by that is r square. We know that this is gm by r square. So if you place here total energy, that will be equal to minus g m m r by uh, r square into 4. So if here you get here, that is g minus g r by 4. You are going to get here minus g r small m by 4. You are going to get here this. That means the important point here is that the satellite, when it is satellite, when the satellite is present at a height which is equal to the radius of the earth, at that point your acceleration due to gravity is working there. Your acceleration due to gravity is working there. That means at that height we can eject a satellite. Then most probably the satellites are ejected at about this height, because here acceleration due to gravity is working there. That means to the level where the acceleration due to gravity is working, on up to that height you can place the satellite, and it will be orbiting around the earth. But when your total energy is zero, when your total energy is zero, that means at that point is g is zero. And when your total energy is zero, that means your g is zero. That means the satellite is away from the, that means it cannot remain around the earth. It will move away from the earth. It will move away from the earth. That means if your total energy becomes zero, it will, then your gravitational, this g will becomes to zero. G will becomes zero. There is no gravitational force acting on the satellite, and it will escape from the earth. It will escape from the earth. Elastic potential energy, this is your elastic potential energy, that is equal to half stress into strain. That is half stress into strain. This is your elastic potential energy. And now the most important thing here is the surface tension. Remember, surface tension. Surface tension. Here, surface tension, it can be expressed in two ways. The first is that in terms of force, it can be written as force per unit length, that is F by L, force per unit length, F by L. And in terms of energy, it is surface energy per unit area. It is surface energy per unit area. That means surface tension, it can be expressed in two ways. In terms of force, it is force per unit length, and in terms of energy, it is surface energy per unit area. So, for water drop, for water drop, the formula becomes uh, that means here your internal pressure must be greater than the external pressure. So Pi minus P naught is equal to 2 sigma by R. R it is the radius of the water drop, where sigma it is surface energy per unit area. This is sigma, it is surface energy per unit area. This is an import. So most of the student gets confused with surface tension, with surface tension, because surface tension it can be expressed in two ways: force per unit length or surface area per unit energy. That means if the film is stressed, then here comes your force per unit length. That means at the same time your if the film, any fluid film is stressed, then we go for force per unit length. And next important point here, in order to minimize surface energy, in order to minimize surface energy, minimize surface energy. In order to minimize surface energy, the water surface takes the shape of a sphere. The water surface takes the shape of a sphere. Minimize, it takes the shape of a sphere. These are important why problems some are asked here. I am giving you the concept which will help you to solve the problems. Capillary rise. Capillary rise. Here this is the fluid up to the capillary rise. Here this is the PA, atmospheric pressure, here PO, and this is the height. Height. That means PA minus P naught, PA minus P naught. What is this? This is the excess pressure. PA minus P naught, it is the excess pressure. PA minus P naught is the excess pressure. And in order to balance this excess pressure, the liquid rises through the height h. So this excess pressure is equal to h rho g. This excess pressure is equal to h rho g. This is the main basic concept of the capillary rise. Why the liquid when column rises to the height h? Because of this excess pressure here, the outside this curve PA, and on the other side is P naught, so there is difference in pressure. So this difference in pressure is the excess pressure. In order to balance this excess pressure, the water rises to the height h. So this excess pressure is equal to h rho g. Again, the total pressure uh, at any height of a liquid, total pressure, that is at any height, it is equal to P atmosphere plus rho gh. This is the height. Up to height we require rho, it is the density, and h, this is the height. To that height where we require the pressure, to that height where we require the pressure. So total pressure at a height, sorry, it is better to say depth. It is better to say depth. Total pressure at any depth will be equal to PA plus H rho g. This is the total pressure at any depth. Now here there is also an important equation, that is a continuity equation. continuity continuity equation. I have selected all these theories because these are practically used theory, and the questions are practically set, questions are set where there is a practical application. Now here this is the continuity equation, that is a1 v1, v1 which is the velocity, is equal to a2 v2. And why this is important? Because on this continuity equation, nozzles are designed. On this continuity equation, nozzles are designed. Nozzles are designed. On this continuity equation, nozzles are designed because you see that the nozzles are on this shape. Here, area A1, this is A2. So here your this is velocity v1, this is velocity v2. So here you see that a1 v1 is equal to a2 v2. So since a1 is greater than a2, so to balance this, your v2 is greater than v1. So your output velocity of the fluid will be higher than the input velocity, and so it helps in cleaning purposes. Now, next theory we move to, this is also an important theory, that is if there is heat transfer, if there is heat transfer in the same state, if there is heat transfer, heat, say, um, instead of heat transfer, it will be better to say that heat required to raise the substance, to raise the temperature of heat required to raise the temperature of a substance to say some degree, heat required to raise the temperature of a body or a substance or a fluid to some degree, and it must be in the same state. Remember that it must be in the same state. So the heat supplied Q will be equal to ms delta T, where S is the specific heat capacity, speci one minute, specific heat capacity. Your S is the specific heat capacity, heat capacity, heat capacity of the substance. I am repeating the same thing. If you want to increase the temperature of a body by some degree, and this phenomenon must happen in the same state. That means either it is in solid state, in liquid state, in gases. It must be same state. Then the heat required or supplied will be the formula you have to take, ms delta T. But if there is change in state, then your heat supply will be ml. L, it is the latent heat. This is the latent heat. This is the latent heat. Latent heat. That means this is very, this is the basic, and you must remember. Suppose this is ice. Here this is ice, and you have increased its temperature to say some degree. That means when you increase it to some degree, it converts into liquid. First of all, to some degree, say. First of all, initially it is in 0 degree Celsius. Initially, it is 0 degree Celsius. And say 0 degree Celsius. Initially, it is in 0 degree Celsius. Let us take in Mhm. Let us take in this way. It will be better to explain you in this way. When there is change in state from ice to water, from ice to water, your heat required will be ml. You have to apply this formula ml. But if there is rise in temperature, if there is rise in temperature, it is ice, and if it is rise in temperature here, and your state is in solid state ice, then you are going to use the formula ms delta t. ms delta t. Now, if there is thermal conductivity, thermal if there is thermal conductivity through a conductor, through a conductor, if there is thermal conductivity through a conductor, that means heat transfer, that is heat transfer, then H is equal to Ka T1 square minus, no, not square, sorry, T1 minus T2 T by L. That means here this is a temperature at T1 and another sorry, another it is at temperature T2. This is the conductor of length L and its cross-sectional area is A. So heat transfer through the conductor, this K is a constant and T is the time taken. T is the time taken. So remember, if the question is that is the thermal conductivity through a conductor, then you have to use this formula. And if the question is thermal conductivity by the help of radiation, then your formula will be different. I'm going to write the formula. So here you see you have to read the questions while solving the problems. If there is thermal conductivity through a conductor, then we use this formula. And if there is a thermal conductivity by the help of means heat, that means if there is heat, this is heat transfer. It is better to say if there is heat instead of thermal conductivity, it is better. So if there is heat transfer by radiation, then we go for a different formula, which I am going to write it below. The formula is this is by radiation, your radiation, radiation. The formula is H is equal to radiation. Your formula is epsilon sigma T1 to the power of 4 minus T0 to the power of 4, where this is emissivity. This is emissivity. Emissivity. This is emissivity. This is for which are not a perfectly black body. It is not a perfect black body. Black body because it has been found that in our bodies different from black bodies, it does not emit the whole quantity. It only emits a fraction of it. It only emits a fraction of it. So this emissivity comes here, and if it is a black body, then this term is deleted. There is no this term. So the main point here is that while solving problem, that is if there is thermal conductivity, heat transfer through a conductor, we take this formula, and if there is heat transfer through radiation, we take this formula. And in heat transfer, most of the problem is solved by just a single law, that is heat lost is equal to heat gain. This is the main basic concept. Heat lost is equal to heat gain. Now you all know that here this is a Q positive Q charge. Here this is a positive Q charge and positive, so field direction is radially outward. This is the electric field. Here this is the electric field. So here this is any point A and point B, a plus Q charge. If you bring here from A to B, so there is difference in potential energy. UB minus UA. There is difference in potential energy difference. This is potential energy difference. There is potential energy difference. Now, if you divide this by Q, UA by Q, this becomes VB minus VA. This is again this. Now it converts into potential difference. Now it gets converts into potential difference. Now it gets converts into potential difference. And potential difference. And now, if you bring this from infinity to the point B, then it will be UB minus U infinity by Q. So here U infinity is 0. So this becomes potential at a point. This becomes potential at a point. This becomes potential at a point, means at B. So here you remember that your potential, it is a scalar quantity. Potential is a scalar quantity. Is a scalar quantity. Potential is a scalar quantity, and V is equal to Q by 4 pi epsilon naught R. I want to tell you an important thing between electric field, your electric field and potential. Whether the charge is plus Q or minus Q, it does not matter. This electric field is equal to, your electric field is equal to K that means 1 by 4 pi epsilon naught, KQ by your R square into I cap. Let me take this Q. KQ by I cap. Because one minute, I have left one. I will tell you later on, just now. So this KQ by R square, because your electric field is equal to QE. QE is equal to F. So E is equal to F by Q, electric field. So because of this Q cancels out and this is KQ by R square. Here, one thing you remember that this is scalar but this is vector. Whether the charge is plus Q or minus Q, remember in solving question, whether the charge is plus Q or minus Q, it will be always positive. The direction of the electric field will be determined by this I cap, by the unit vector. Whether it is negative or positive, this will be determined by this I cap. But whether the charge is Q positive or negative, you have to write always positive value. Only that the electric field will be negative or positive, it will be determined by this uh, direction I cap. But in potential, since it is a scalar, for positive you will write plus q, for negative you will write minus q by 4 pi epsilon naught r while solving the problems. You remember this. Your electric field direction, which is whether it's negative or positive, it will be determined by this unit vector. But this, since this is scalar, for plus q you have to place plus q, for minus q you have to place minus q. While solving problem, then you will find no difficulty to solve potential or electric field. And one thing I left here is that this is equal to, this is work done, W by Q, this is V potential. Now let us take another topic. Another topic. These are the basic. You remember that here this is a charge Q, a body with charge Q, and if an uncharged body, this is an uncharged body is brought near it, then this charge will be divided equally between the two bodies. That means it will become Q by 2, Q by 2. Remember this. When an uncharged body is brought, this is charged, and this is uncharged. When an uncharged body is brought near a charged body, the charge will be divided equally. That means it becomes Q by 2 and Q by 2. Now there is another important point I want to tell you. These are the basics which I'm dealing here, and it is type of a crash course. This is part 1, and here you see capacitance. You know this formula, epsilon naught A by D. This is capacitance, formula of capacitance. And again, capacitance is equal to Q by V. So what results are you going to get here? This is this. That is epsilon naught A by D is equal to Q by V. That means D is proportional to V. That means if the distance between the plate capacitor increases, your potential increases. And since potential increases, your charge also increases. Your charge also increases. So these are the conclusions. A, it is the cross-sectional area. D is the distance between the two plates. So that means as the distance between the two plates increases, your potential increases. That means your charge also increases. So, and another important point here is that you must remember that if you impose a dielectric medium, it is nothing but it is a insulator, then your capacitance of the capacitor increases. Your capacitance of the capacitor increases. Now see, magnetic field intensity, that means field after all, magnetic field intensity at any point, at any point outside, at any point outside outside a cylindrical wire, outside a cylindrical outside a cylindrical wire, that means R is greater than A, that means R is greater than the radius of the cylinder, R the point, then your magnetic field is equal to nu naught I by 2 pi R. And second, at the surface, it is B is equal to nu naught I by 2 pi A. And inside the surface, inside the surface. Inside the surface, it is nu naught I r by 2 pi a square.